temperature. The top method for problem solving in chemistry is going to be what method? The dimensional analysis. But you can't solve all problems using dimensional analysis. Well, we also have to use other problems solving methods, like like for example, an algebraic equation. An algebraic equation would be something like temperature. If we're looking at temperature, the algebraic equation is degrees Fahrenheit is equal to 9/5 degrees C plus 32 degrees. And so we can interconvert between Fahrenheit and Celsius, like this. And so yesterday we did a calculation. The calculation was that if it's 25 degrees C, what was the Fahrenheit temperature? If we tried dimensional analysis, we could try it out and see what happens. Because there's no desk drawer there, for the lab station. Maybe try to find an open one. And then we'll do that. So yesterday we did this calculation. Did we do this calculation? And it came out to what, 77 degrees Fahrenheit. Just a little warm. They call that room temperature. Actually, what is the temperature of the room today here? It's warm inside here. And we had a thermometer mounted there. But I'm not familiar with this lab. They must have moved it somewhere else. But we want to get familiar with the lab because of this common safety. In fact, how many people missed lab last week? I have to, and then depending on how that safety quiz went, I'm going to ask some people to watch the safety video today. So we'll look at that probably at the end. So 25 degrees C, we got 77 degrees Fahrenheit. And so we could try, there is a relationship between Celsius and Fahrenheit. The relationship between Celsius and Fahrenheit is that for every 180 degrees Fahrenheit, we have 100 degrees C. And so if we have 100 degrees C, then we have 180 degrees Fahrenheit, correct? Do you remember seeing this ratio? This ratio came from the slope of the relationship. And so does this mean, in other words, does this mean if it's 100 degrees C, does this mean if it's 100 degrees C, then it's 180 degrees Fahrenheit? Is that what that means? Okay. I remember this. We had this ratio between Fahrenheit and Celsius. Do you remember going through the derivation of that? Delta Y, delta X? Remember that? And we came up with this ratio that we went out X 100 degrees C, we went up Y 180 degrees Fahrenheit. And so it seems like for every 100 degrees C, we have 180 degrees Fahrenheit. And so that's the relationship. In fact, if you think about a 1 degree C change, I have this car, and I think it's kind of annoying. But this car has a temperature adjustment in Celsius. This is a German car. So it goes from, let's say, I'm trying to adjust the temperature. And so if you have it at like 22, the next temperature up is 23. And the problem with that car is 22 is too cold, but 23 is too hot. It's too hot because that jump from 22 to 23 is actually a 1.8 degree jump in Fahrenheit. You know? And so that's almost a 2 degree jump in Fahrenheit. So that'd be like the difference between 74 degrees C and 76 degrees C. You know, you can definitely tell the difference in temperature, right? Between 74 and 76. Or 78 and 80. You know, 78 might be comfortable, 80 might be a little too warm. In this room. This room feels like 78. And so this is correct. You know, for every 1.8 degrees Fahrenheit, there's 1 degree C. And so can't I use this in a problem like this? For example, 25 degrees C, and then I use this. Well, I know that there's 1.8 degrees Fahrenheit for every degree C based on the ratio, based on the slope I got, right? And so this gives me, what does this give me? This gives me (25 times 1.8) is what? 45. Okay, 45.0. Is that it? Okay, 45.0. What I said yesterday is if I'm allowed 2 sig figs, I want to see 3 sig figs, and then I wanted you to round it. And so I'd go 25 degrees Fahrenheit, which is equal to 45 degrees to 2 sig figs. Now, when we look at this, is this right or is this wrong? In other words, is this ratio that we got, 180 degrees Fahrenheit for every 100 degrees C, is that correct or is that incorrect?
That's correct.
Just get more information.
Do we have to add the 32? It depends. It depends on what I'm talking about. This is the right answer if I'm looking for something. In other words, if I'm looking for the absolute temperature, you know, what is the temperature, then this is the wrong answer because, you know, I'm missing the 32. But if I'm looking for something else, then this is correct, you know. In other words, let's say I'm at room temperature, 25 degrees Celsius, room temperature, 77 Fahrenheit. Okay. And then if I go up from 25 degrees Celsius to 50 degrees Celsius, so the temperature increased by 25 degrees Celsius. If the temperature increased by 25 degrees Celsius, what did the Fahrenheit increase by? 45 degrees. And so here, this 25 degrees Celsius change would be equivalent to a 45 degrees Fahrenheit change, because Celsius is a bigger jump in temperature than a degree Fahrenheit. And so what I end up with is, what is 45 and 77? Well, 40 and 70 is 110, and 110 plus 12 is 122. So I'd end up at 122 degrees Fahrenheit. And so it is correct. And so I could use a conversion factor like this if I'm talking about what? So I could use dimensional analysis if I'm talking about change. If I'm talking about a delta t, this has to be a delta t. Remember the slope. This came from delta y over delta x. So if I'm looking at the change, so for example, if I had a 1 degree C temperature increase, I changed my heater to 1 degree C temperature increase, that would bump up the Fahrenheit temperature by 1.8 degrees. And so, but really, if you want a heater, the best one is to get one that does half a degree C. So it goes from 22 to 22.5 and then 23. That would be much better than the heater I have. The heater I have just jumps from 22 to 23, which is a bit too much. And so if we're looking at delta T's, we could use dimensional analysis, because a 25 degree C temperature change, this delta T, is equivalent to a 45 degrees Fahrenheit temperature change, which is a delta T. And so here, dimensional analysis is no problem. But if I'm looking at, a temperature like 25 degrees C, the ambient temperature, or whatever, if I'm looking at the ambient or the sample temperature or whatever, the measured temperature, if I'm looking at something like this, then I have to correct this. Dimensional analysis would work if the Celsius and the Fahrenheit temperature scales had the same 0 point. They don't have the same 0 point. 0 degrees Celsius up here, but 32 on the Fahrenheit scale, we're at 32, and so we'd have to drop it down another 32 degrees Fahrenheit in order to get to the 0 on the Fahrenheit. So the zeros don't coincide. Since the zeros don't coincide, we have to do kind of a dimensional analysis, and then as was mentioned, we have to add 32 to compensate for the difference in 0 points. And so when we're doing the ambient temperature, we have to do it algebraically. We cannot use dimensional analysis. We have to use the algebraic equation. Degrees Fahrenheit is equal to 9/5 degrees C, or 1.8. This is 1.8, or 1.8 over 1 degrees Celsius plus 32 degrees. Again, I'm ignoring units because this is traditionally what's done, but in this type of equation, we can include the units, and the units would work out because we know that the actual units of this is 1.8 degrees C for every 1.8 degrees Fahrenheit for every 1 degree C, or 9 degrees Fahrenheit for every 5 degrees C. That'll be another way of thinking about it. So for every 5 degrees C temperature change, there'll be a 9 degree Fahrenheit temperature change. All right, so here, if we're looking at delta T, we'd use dimensional analysis. If we're just looking at what is the temperature, then we would use algebra, the algebraic equation for this, although this is algebra as well. Now, we're going to encounter some equations like this temperature equation, like this, some others, like something called the ideal gas law, and the combined gas laws, which we'll see in the next chapter. All right, then sometimes we have, okay, that was the algebraic equation. Sometimes we have multiple unknowns. And so when we're trying to think about it, is there a temperature where the degrees Fahrenheit is equal to the degrees C? Is there a temperature in which the temperature in degrees Fahrenheit is equal to the temperature in degrees Celsius? So I'm just saying temperature T, capital T. Lowercase t is usually used for time. So is that possible? Yes or no, do you think? I don't know. We can find out. We can find out by just setting this out algebraically. And so how would we do that? Well, how we do that is, okay, we want them to be equal. And so if the temperature in degrees Fahrenheit is equal to the temperature in degrees C, we call this equation 1. We have two unknowns. We have two unknowns. We don't know what the temperature is, but we only have one equation. So we need another equation. What's the other equation we can use? Should we use the kind of the dimensional analysis type thing? that we did, remember the dimensional analysis type thing we did for the chlorinating solution in the pool? And we used the dimensional analysis, the long one, although I didn't write it all out, as our second equation. Basically, our first equation is that the total volume of pool water is equal to the volume of pool water originally, 18,000 gallons, plus the volume of chlorinating solution. But for something like this, what would the second equation be? Yeah, just this. So this is the temperature in degrees Fahrenheit is equal to 9/5. Now, if I wanted to include the units, which I could, this would be 9 degrees Fahrenheit for every 5 degrees Celsius times the temperature in degrees Celsius plus 32 degrees Fahrenheit. And so now the units would work out, because if I plug in the temperature in degrees C here, the degrees C cancels, and that leaves me with degrees Fahrenheit, which is what I want. But I don't know why this is not normally done. It's probably not normally done because most people just memorize this equation, so it's easy to memorize it without the units. And just make sure you have it memorized correctly. But anyway, this is an easy equation to derive, so it's not one that really needs to be memorized. Derive it. And so this is the second equation. So what we'll do is we'll just do substitution. So we can either substitute temperature in degrees C or temperature in degrees Fahrenheit. Either one. And so we'll go ahead and substitute maybe temperature in degrees Fahrenheit here. And so we get the temperature in degrees Fahrenheit is equal to 9/5. Now this will be degrees Fahrenheit, degrees C. Okay, the temperature in degrees C is equal to the temperature in degrees Fahrenheit. So this has got to be temperatures in degrees Fahrenheit plus 32 degrees Fahrenheit. This is this kind of substitution. Here, maybe the units don't quite work out, but essentially it works out because they're equivalent. So if they're equivalent, then the units drop out, but it doesn't matter. It's Fahrenheit or Celsius, it's the same number. And so we're going on from here, and we just solve for temperature in degrees Fahrenheit. So probably the easiest thing is subtract 32 from both sides, maybe? Is that the easiest? Yeah, let's subtract 32 from both sides. So I'm going to have minus 32 degrees Fahrenheit, and let's add 5/5, or subtract 5/5. That's probably easier. Let's subtract 5/5 from both sides. 5/5 temperature in degrees Fahrenheit, and so that's going to give me 4/5 degrees Fahrenheit, and then solve for the degrees Fahrenheit. What's minus 32 times 5 divided by 4? I'm sorry? Is it negative 40? Negative 40.0? Negative 40.0 degrees. And so what that means is that negative 40.0 degrees Fahrenheit is equivalent to negative 40.0 degrees Celsius. So if I had two thermometers and I put them in negative 40 degree substance, both thermometers would read negative 40. Does that make sense? Is there a way we could double check this?
Subtract 5 from.
Well, 5. I just what I did was here. I skipped some steps, and so I have degrees Fahrenheit is equal to 9/5 degrees Fahrenheit plus 32. And so I could have done this. I could have subtracted 9/5 degrees Fahrenheit from both sides. But instead, I subtracted 1 degree Fahrenheit from both sides. To get it in the common denominator, I just multiplied by 5. And so rather than calling it 1, I called it 5/5 and then subtracted it from both sides. And so 5/5, 9/5 minus 5/5 should give me 4/5. And then I took the 32 and subtracted it from both sides, just to do that. And so in other words, it was this: 9/5 minus 1 equals what? And so if I do 9/5 minus 1, what does that equal? Well, I got to get these in the common denominator. And so this is going to be 9/5 minus the common denominator is 5. And so if I want a 5 there, then I have to have 5 here. I'll multiply top and bottom by 5. And then I get the common denominator. And so 9/5 minus 1 is actually equal to 4/5. So that's what I did to get it. But we can double check the answer. I mean, is that correct? I don't know. How can we double check the answer? Well, we could double check it just by plugging it into the equation. And so if I plug it back into this equation here, and then C, degrees Fahrenheit is equal to 9/5 degrees Celsius plus 32 degrees. And so what I'm going to do is I'm going to plug in here for degrees Celsius minus 40 degrees. And so go ahead and do that. Take minus 40 times 9 divided by 5 plus 32. Well, what do we get? So this is my degree C. So if I do 9 times 40 divided by 5 plus 32, I get 40 degrees Fahrenheit. You see that? Okay, what were some of the other problems that that we saw yesterday? Well, one of the other problems was this. Is there a next example? Is there a what was it, Fahrenheit or Celsius? Is there a Fahrenheit temperature that's twice the Celsius temperature? And so if I have two thermometers here measuring the same thing, and so here I have my Celsius temperature, here I have my Fahrenheit temperature. And let's say my Celsius temperature were X degrees Celsius. Okay, is there a temperature at which the Celsius and the Fahrenheit, in other words, the Celsius is half the Fahrenheit is twice the Celsius? So for example, if the Celsius were reading 100 degrees, the Fahrenheit would be reading 200 degrees. Maybe 100 degrees is the temperature. But is there a temperature in which the Fahrenheit would be reading exactly twice that of the Celsius? Well, why don't you try to solve this one using the two equation, two unknown method. I'll give you a little bit of time here.